we're going to continue our discussion of resonance and how resonance can affect the acidity of a molecule, an organic compound in particular. And our book that we use does not use the term resonance so frequently for this effect, but it will use the term electron delocalization. So electron delocalization is something that's really important, that sometimes the electrons are free to move from one end of the molecule to the other, whereas other times the electrons are stuck on the atom they're stuck on. So if you have one of the ways to get electron delocalization is through resonance. So those terms sometimes are used interchangeably by some people. Other people lock on to one term or the other, but these two concepts are very related. Resonance, in my mind, causes the electron delocalization, and they're both important for understanding the acidity of different molecules. So we had talked at some point about acetate and acetic acid and ethanol and ethoxide, and one other compound that's worth looking at is phenol. So phenol, C6H5OH, would also be called phenyl alcohol, I believe, and there's other words for this, carbanols and whatever, but we don't want to get too into the ancient language. But phenol, C6H5OH, this phenyl group is very important in organic chemistry. It's an aromatic group, essentially based off of benzene, or a derivative of benzene, you might say. And the 6 carbons are in a hexagonal ring. Very nice. Bond angles render great stability for this. And then there's 3 double bonds, causing the aromaticity, we would say, which is a stabilizing factor we won't talk about today. And then in this case, one of the substituents on this 6-membered ring is an OH group. So this would be phenol, or phenyl alcohol. The phenyl group is this guy. And because these carbons are double bonded to each other in alternating fashion, there's possibilities for resonance. So these pi electrons can move through the ring. And that's going to be something we'll illustrate as we write out some of these resonance forms. Now phenol is acidic, right? So phenyl alcohol. Here's the phenyl group, is what I circled there. This is the alcohol group. So you could see where the name phenyl alcohol would come from. And this normal alcohol group is pK about 16. But when you attach the phenyl ring, that's going to make its pK lower, or this is more acidic and has a pK of 10. And where we're going to get into the resonance effects is by drawing the structure of the conjugate base and then looking at the various resonance forms of the conjugate base. So the way we get the conjugate base is to, again, release the H+, so the hydrogen is going to leave without its electrons, and the electrons in the bond are going to go to the atom connected to hydrogen, in this case the oxygen. So now we're going to redraw the glorious phenyl group with its 3 double bonds, 5 hydrogens, and 6 carbons, but now the oxygen attached to the phenyl group is going to have a minus formal charge, as the hydrogen has left without the electrons as an H+, the electrons have had to sit on that oxygen. Now if this were localized, if those electrons couldn't go anywhere, then this would be a lot more like hydroxide or ethoxide and would be a fairly good base. But these electrons can now move by virtue of the fact that they're next to double bonded species. So we saw this with acetate. There was a carbonyl here, and the oxygen electrons could move towards the other oxygen electrons. In this case, we're going to move the oxygen electrons to carbon, which is less stable and less likely but it's still a reasonable factor that we need to consider. So we're going to look at resonance forms of this conjugate base of phenol, which I would call phenoxide. Right? So here we go. And this is a little tedious, but it gives us good practice in drawing hexagonal structures. In the rest of the course, you'll probably be using a shorthand for the phenyl group, where you're not going to write out every carbon, but since I'm going to show the mechanism of forming the resonance forms, I'm going to need a little more detail. Alright, so this oxygen has the negative charge right now, but one way to move the negative charge away from this oxygen is to move a lone pair in to form a bonding pair and make a multiple bond between this carbon and this oxygen. And if we do that, that would mean that this carbon has more than 8 electrons around it because it's already got 8 electrons. If I move 2 more into its environment, that would be 10, but since we have a multiple bond here that we can push off and turn into a lone pair on that carbon, this is possible to now delocalize or move the oxygen electrons away from the oxygen a little bit. So again, another hexagonal ring of the 6 carbons, but now we're double bonding this carbon to the oxygen. The rest of the molecule is mostly unchanged. Right, so that's something I have to be very careful of, not to change something that's not changing. Like these 2 double bonds, I don't want to forget those. But now we've moved the multiple bond from here, we've pushed it into being a lone pair on this carbon, and now that's where the formal negative charge is. So the negative charge that was on the oxygen, by moving a lone pair from the oxygen to make a multiple bond, and to move a multiple bond to be a lone pair on the carbon, we've now moved an electron pair onto the carbon. The electron pair on the more electronegative element means this is the favored resonance form. Right? It's going to be more stable, and is probably going to be, on average, the better representation of the molecule if you had to choose one structure. But moving some of the electron density onto the carbon is also reasonably favorable. So it's enough to consider this resonance form as a contributor to our understanding of the overall structure. And then this negative charge on the carbon, we might want to move off that carbon. So we could move it back to the oxygen, go back to here, or we could take this lone pair and make a multiple bond there, and then in order to do that we have to push electrons off of this carbon, or it'd get up to 10, so we're going to move one of these bonds to be a lone pair on this carbon. So every other carbon, it looks like, can go ahead and take on the negative charge in one of the resonance forms. Again, we're going to redraw the hexagon. We're going to leave much of the molecule the same as it was, but now you can see we're pushing a bonding pair to be a lone pair on this carbon. Now that's going to be a formal negative charge. We're going to move the double bond to here. Each carbon still has a hydrogen except the one that's double bonded to the oxygen. So now we started with the negative charge on the oxygen. We moved it to what we would call the alpha position. This is a carbon that's our reference. The first off the carbon is alpha. So let's put the negative charge on this carbon, and then we can also move it 2 carbons over onto this carbon. So some of the carbons can be more negatively charged. As we create the resonance forms, we show which carbons can hold some of the negative charge. Go ahead, push that up a little, get everything on the screen. And then one final push to get our 4th resonance form is this negative charge can move further around the ring, become a double bond here, and then this double bond is going to move to form a lone pair on this carbon. So again, hexagonal structure. We had our double bond to oxygen here, hydrogen here, double bond here, hydrogen here. Now the lone pair that was here is going to form this double bond. And then this carbon has got its octet obeyed. This double bond that was here is moving onto this carbon, which will now have the negative charge. So we can follow along with the electrons. How they can move is shown by the electron arrow pushing, and we can put the negative charge on the oxygen, the carbon next to the carbonyl, the carbon across from the carbonyl, and then the carbon next to the carbonyl on the other side. So there's 4 different places the negative charge can reside. The best place is on the oxygen because it's most electronegative, but we can't totally ignore the contributions of carbon to take the negative charge. Now, I've mentioned before there's something called the resonance hybrid, which in general I don't really like, but it shows that there's electrons moving around the ring and out to the oxygen. So there's these pi system electrons are moving all around the ring and to the oxygen. I can't tell from the dashed line how many electrons are in the structure, but the way that the negative charge is distributed, if you look at computer models and different reactivity studies, it looks like the oxygen gets 7/10 of the negative charge, and then the carbon next to the carbonyl gets about 1/10 of the negative charge, and then the carbon across from the carbonyl gets about 1/10 of the negative charge. So this oxygen is still going to be the best thing to attract an H+ in terms of the basicity of this anion, but rather than being a full negative charge like in ethoxide or hydroxide, some of the negative charge is distributed into the ring, reducing the effectiveness of this as a base. So this is a weaker base than something like OH-, which makes phenol a stronger acid than water. So when you compare the basicities here, the full negative charge, the localized negative charge, makes this quite basic. This is a little less basic because the best place to put the hydrogen is 7/10 of a negative charge. And so comparing the pKs of the acids, this guy, weaker base, the phenoxide, is a weaker base than hydroxide. And that means water is a weaker acid, and the phenol, now I'm going to use the shorthand, the phenol, this is a shorthand for the phenyl group, the phenyl alcohol, since its base is weaker, it's a stronger acid, pK equals about 10, water, pK equals 16. So stronger base, weaker acid, weaker base, stronger acid. And so it's a little complicated, and if you really want to master this, what I suggest you do is practice drawing the conjugate base of phenol as just the oxygen having the negative charge, and then practice pushing the lone pair to make the bonding pair to make a lone pair, and see where that pushes the negative charge. You know, if you memorize sort of the answer, the negative charge should get pushed to 3 different carbons, but showing in detail which electrons get pushed where and when to form the 3 resonance forms with the carbon having the formal negative charge. A little practice there might be necessary to get this. So that's, again, a fairly long description of one ion's resonance forms. But if you're going to go into reactions of aromatic groups, understanding this electron pushing is going to be really, really important. So I hope this was clear enough and helpful. And we'll talk more about acidity and predicting pKa's in a little bit.